Open circuit test and short circuit test. This is the circuit diagram for open circuit test. LV side and HV is kept open, or it may be connected through high resistor and voltmeter. If we keep the transformer secondary or HV side open, then the terminals must be properly insulated during testing. The main objective of this open circuit test is finding R0, X0, I0 and P0. P0 is no load losses. So from this open circuit test, we get the constant losses, total iron losses and dielectric losses. Primary side copper losses, these are very small. The supply is given through auto transformer, voltmeter, wattmeter and ammeter. This is the open circuit test. It is performed at rated voltage only. The wattmeter, low power factor wattmeter, approximate range is 0 to 0.5, lagging. So this wattmeter will read total losses of the transformer. Voltmeter will read the voltage across the LV winding. Ammeter will read no load current. The wattmeter gives no load power losses P0 equals to P0 I0 cos phi naught. The ammeter gives no load current I0, and this term I0 into cos phi naught is considered as IW, working component. So from these two terms, I0 and IW, magnetizing term can be calculated. This is magnetizing term current IM equals to under root I0 square minus IW square. The magnetizing current component I0 into sin phi naught. The voltmeter gives the reading V0. So R0 equals to V0 by IW and X0 equals to V0 by I magnetizing component. This is the branch I0, IW, IM magnetizing current. This is the vector diagram. This is the primary side voltage V1, flux in the core, magnetizing current, working component, no load current, angle between supply voltage and no load current. The voltmeter on secondary side will read back EMF E2. So this is the term E2 and this is term E1. The voltmeter on the secondary will read back EMF E2. Transformation ratio K can be calculated from this open circuit test condition. K equals to E2 by E1. Voltmeter on HV side will give you E2. Voltmeter on LV side can be approximately considered as E1. So from open circuit test, R0, X0, I0 and P0 are calculated. Short circuit test. This is the circuit arrangement for short circuit test. Devices are connected on HV side and LV is short circuited through thick wire, or it may be connected through ammeter. The objective of short circuit test: finding R01, X01 and total copper losses. This test gives total variable losses such as copper losses and small portion of iron losses and small portion of stray load losses. The supply is given through auto transformer. As we are conducting short circuit test, so total short circuit current can flow through the circuit only by applying 10% of rated voltage, because we are applying this voltage on HV side. So by applying 10% of rated voltage, full load short circuit current will flow through the circuit. Ammeter will read the current, wattmeter will read the total copper losses, voltmeter will measure the voltage across the HV terminal voltage. The short circuit test is conducted with reference to rated current. Wattmeter gives total copper losses, voltmeter, ammeter readings. From these readings, we are obtaining impedance Z01 equals to V by I. From the wattmeter reading, R01 is obtained. From these two results, X01 is calculated. X01 is equals to under root Z01 square minus R01 square. This is the vector diagram. Short circuit current I2 and X02, I2, R02. This is current and impedance triangle. So the data obtained from this short circuit test, this is useful for voltage regulation calculations. The voltage regulation formula I2 R02 by E2 cos phi plus or minus I2 X02 by E2 sin phi. R02, X02 are calculated from this short circuit test. So this is the equivalent circuit. Total resistance referring on primary side, total reactance referring on primary side. This is the short circuit current flowing into the circuit. Synchronous test or back-to-back test. This is mainly for to find out the temperature rise in the transformer. This test has to be conducted minimum 4 hours at full load. So from this test, we can get all the results which are helpful for finding the efficiency of the machine, voltage regulation and heat. This is also known as heat run test. HRT, heat run test. This is the total arrangement for heat run test. Required 3 transformers. One is regulating transformer. 2 identical transformers. These are 2 identical transformers. Connections must be as per the circuit diagram. LV sides are connected in parallel across the source and HV sides are connected in series opposition. So this is the transformer 1, this is transformer 2. The primaries are connected in parallel where the secondaries are connected in series opposition. This is primary side voltmeter, ammeter, wattmeter. This is secondary side voltmeter, ammeter and wattmeter. On the primary side, this wattmeter will read total iron losses of both the transformers. On the secondary side, this wattmeter will read total copper losses of both the transformers. So from this test only, we are able to get all the results of open circuit test and all the results of short circuit test at the same time. Here the supply is given on both LV and HV at the same time. So this condition is considered as full load condition. And the open circuit test and short circuit test parameters all we are able to get at the same time. The T1 is test specimen. T2 is identical transformer which is required to perform this test. So this type of test can only be possible in factories, not at the site condition. So during testing, we have to record OTI, WTI, body temperature also regularly at every 30 minutes and iron losses, copper losses to be calculated and the same must be recorded. So open circuit test, short circuit test and synchronous test, these are important tests, and other tests such as polarity test and voltage ratio test and other tests. Polarity test, this test is very important to connect the transformers in parallel. So this has to be verified before connecting the transformers in parallel or in series condition. So this is the approximate diagrams for additive polarity and subtractive polarity. This is primary side and this is secondary side. On the primary side, we are assuming dot and this is current direction. On the secondary side, we are assuming a dot and this is the current direction. Here we are assuming that for this current to cross this winding, it takes time t seconds. On the secondary side, for this current also, it takes t seconds to cross this total winding. So on the primary side, the current is entering from the top and it takes time t. On the LV side, the current is entering from the bottom and it takes time t to reach the top. So during the same time period, on both primary side and secondary side, the currents are entering in opposite directions. So the opposite polarities will appear on the windings. On the primary side, polarity is plus and minus. On the secondary side, the polarity is plus and minus. So during this period, as the currents are entering from opposite directions, the circulating currents will flow in the windings, which cause very high stresses in the windings and insulations. So this is additive polarity. If we take one more voltmeter VC and connection is made in this form, and if we apply Kirchhoff's current law in outer loop, then this is additive polarity because VC equals to VA plus VB. This is additive polarity. This kind of arrangement is not recommended. For subtractive polarity, on the primary side, we have considered dot here and this is the current direction. On the secondary side, we have considered dot here. This is the current direction. So in this case, by the time current entering the primary, at the same time, the current is leaving the secondary. So there are no circulating currents in this case. So this is same polarity on primary side and secondary side. So if we take additional voltmeter VC and apply Kirchhoff's current law on outer loop, then VC equals to VA minus VB because primary and secondary will have same polarities. This is subtractive polarity. This is very much preferred. So during polarity test, we have to find the polarity of the transformer windings for connections. Voltage ratio test. From open circuit test, we can get this data E2 by E1. From short circuit test, we can get this data I1 by I2. The data obtaining from these two tests, we can get this ratio, voltage ratio. These are other tests which we can perform on transformers. Insulation test, insulation resistance test, vector group test, dielectric test, impulse test, partial discharge test, breakdown voltage test, dissolved gases or gases dissolved in transformer oil, parallel operation of transformers. For this, we must satisfy some conditions for parallel operation of transformers. One is same V2 by V1 ratio or K ratio, same phase sequence RYB, same polarity, same frequency, equal impedance. This is for load sharing with reference to MVA rating, same X by R ratio, same tap settings, and same vector grouping. These are the conditions for parallel operation of transformers. Here we are considering our initial load is 20 MVA load. For this load, we have installed a 25 MVA transformer. On later date, the load is increased. 35 MVA additional load is added to this bus. So for this additional load, 25 MVA transformer is not sufficient. So we are connecting another transformer in parallel with this current transformer. So we are considering 30 MVA transformer added in parallel with this transformer. So the total load is 55 MVA and the total transformer capacity is 55 MVA. So to connect this new 30 MVA transformer in parallel with previous 25 MVA transformer, we have to satisfy these conditions for parallel operation. One is V2 by V1 must be same. So on the HV side 33 kV voltage, on the LV side 11 kV voltage. The same must be satisfied. Second, same phase sequence RYB and this is also RYB. Same polarity. The voltages polarities will be same on both sides. This can be identified with reference to dot. And same frequency as our supply voltage is 50 Hz. So both the transformer will operate on 50 Hz frequency only. And same impedance. Here the transformer impedance is 10% and X by R ratio. The same impedance and same X by R ratio must be maintained for new transformer and same vector group also. Coming to load sharing, now the total load is 55 MVA and the total transformer capacity is also 55 MVA. So both the transformers, the 25 MVA transformer will feed 25 MVA load, the 30 MVA transformer will feed 30 MVA load. Now if we assume that 35 MVA load is disconnected from this bus, then the total load on the bus is only 20 MVA. In this case, the 25 MVA transformer and 30 MVA transformer both will share this 20 MVA load in proportion to their capacity. The load sharing depends upon impedance. For example, if we have both identical transformers, then the load sharing will be 50%. But here the ratings are different. One is 25 MVA transformer, the other is 30 MVA transformer. But the impedances are same, XYR ratio also same. Then the sharing is directly proportional to their respective MVA rating. The other case, when the load on the bus is 55 MVA, total 20 MVA plus 35 MVA, but one transformer is going for maintenance, the other transformer has to feed the total load. But for example, we are considering 20 MVA transformer is on maintenance, only 30 MVA transformer will feed the load, but the capacity is only 30 MVA. So out of 55 MVA, 25 MVA has to be disconnected. Only 30 MVA can be fed by this transformer. That is load shedding. So depending upon MVA rating and depending upon delivering load condition, switching on and switching off the transformers varies as per the load condition. That is load shedding. So this kind of arrangement is helpful for increasing the capacity of total system, increasing the reliability, increasing the flexibility. Rating of each transformer, total load MVA plus 30% of future load is total quantity multiplied by 25%, which is design margin. This has to be rating of each transformer. We can have different rating of transformers in parallel also. In that case, the load sharing depends upon rating of transformer and percentage impedance and X by R ratio.